Okay, great. Am I audible? Okay, great. Thank you. Thank you so much for the invitation and for organizers for organizing such a nice workshop and conference. It has been a very nice first week, and now we are diving into the second week. So my talk is about subconvexity of, for L functions of Hilbert modular forms via delta method. And the basic idea behind this work was to try and use a delta method technique to obtain a subconvexity bound for L functions over number fields. This is a work in progress joint with Naomi Tanabe, who is at Baldwin College right now. So I'll be giving a certain background of the rational case that is inspired by the work of Acharya, Kumar, Mathi, and Singh. And the calculations of the number fields will come towards the end. I'll not be able to talk much because it's still a work in progress. Right. So what's the subconvexity bound problem? So in general, let's say that K is a number field of degree D over the rationals, of course. F be a Hecker-Mascus form for SLN OK. If n is equal to 2, we can take it to be a holomorphic form as well. And let's say that LSF is the associated L function. So there's a standard way of associating an L function with a Hecker-Mas or a holomorphic form. And in this talk, we will fix the number field and we will fix the form as well. The analytic conductor that basically measures the complexity of the L function is going to be t to the n times d. So you're raising t, the parameter that you're varying, to the degree and to the degree of the number field. And the convexity bound in this case is going to be the 1/4 power of that conductor. Subconvexity bound is any bound which is less than the 1/4 power. And in this talk, we are trying to get to the while bound. So what's the while bound? There are two major milestones that do appear more and more and again. And breaking those milestones is actually just happens to be quite hard. One is this Burgess type subconvexity bound where the exponent is 3/16 of the this conductor. And the wild type bound where it is 1/6. Both you can see is less than 1/4. So some literature, because I believe this is the first subconvexity bound talk over here. So the first one was because of the work of Weil, essentially written down by Landau, who got the exponent of t to the 1/6 log t for the Riemann zeta function. And if you look at the number fields case, so this is not exactly chronological, but if you look at the number fields case, there is a result by Kaufman and of course also by Heath-Brown, who looked at the Dedekind zeta function, and they also got the 1/6 exponent. So this is also the wild type bound. So there's a rational case, there's a number fields case. I should also mention the result of Sona, who's also got a number fields case. So here, this psi is a Hecker character. It's a fixed Hecker character, it's a fixed number field, and he is varying this parameter t, and he still gets the bound of t to the t raised to the d over 6. Right? So it's still a wild type bound, but it's not just for the Dedekind zeta function, but for any Hecker character L function. So that's the story for GL1 essentially. There's a result of Conry, Ivanic, and Petro Young. So Conry, Ivanic in 2000 proved this bound of Tm to the 1/6. So over here now, chi is a Dirichlet character and it is quadratic. So for the result of Conry and Ivanic, they need this Dirichlet character to be quadratic, and the level is m. And they get the bound of 1/6. And then in the recent breakthrough of Petro and Young, they were also able to get this bound of 1/6. And then their result over the rationals was studied by Balkanova, Frolenkov, and Wu. They used Motohashi type's formula over number fields, and they also basically obtained the same bound where the number field is fixed down. So I'm basically trying to tell you what happened over rationals versus what happened over number fields and so on. In the case of GL2, there's the first result by Anton Good. He proved a result for holomorphic form L functions. And then Tom Merman and Marty Utila, they generalized it to mass forms, Hecker-Mascus forms, but the story is for GL2. And this is over rationals. So if you fix the form and you vary the parameter t, this bound is t to the 1/3, which is t squared to the 1/6. So it's again a wild type bound. And there's a result of Diacono and Garrett, who were looking at the number fields case by different techniques. And their bound is this bound of t to the d over 2 minus delta. Sorry, there should be t to the d over 4 oh no, sorry, it's fine. T to the d over 2 minus the delta. So T to the d over 2 is the is the convexity bound, and they obtained a certain subconvexity bound. So this is the story for number fields if you look at GL2 in the T aspect. Good. And then, of course, there's this breakthrough of Michel and Venkatesh, who gave a uniform subconvexity bound for all aspects for any GL2L functions. And Han Wu went ahead and he explicated those exponents. From what I know, the last exponent that was known is T raised to the Burgess type bound plus theta, where theta is the best known exponent towards the Ramanujan bound. So if you take a Hilbert modular form, you will get theta is equal to 0. If you take a Heck mass form, you will get some different theta. Say again. It should be 3D over 8. Thank you. Sorry. Yeah, this exponent is 3D over 8. Right, so that's the Burgess type bound for GL2. Okay, so again, story for over rationals, over number fields. I should mention the result of Ritabrata Munshi, who proved the bound of m to the 3/4 minus delta. Now over here, pi is any Heck-Maskas form for SL3. There was a result by Xiaoxing Li before that, who proved a similar result for self-dual Heck-Maskas forms. Over here, the mass form is fixed. It's for GL3, that's why you see the cube over here. Chi is varying, it's the Dirichlet character of level M or conductor M. And they obtained certain exponents. That was improved by works of Holovinsky and Nelson, and subsequently by result of Prahalad Sharma, who was looking at GL3 cross GL2, GL1 twist of GL3 cross GL2L functions. So again, these are the story over rational numbers, but the reason I mention this is, and the result, one result that I have not mentioned, is this result of Acharya, Kumar, and Mathi and Singh that I'll reference later. They essentially used the techniques of Munshi for GL2 setting, and they were able to get a wild type bound. So I'll talk about that later. Right. Okay, so this was again the story over rational numbers, but then if you go over number fields, there's a result of Zhiqi. In 2020, he published a result, which if you see is getting a 1/8 saving over 3/4. This falls short of the Burgess type exponent. Over here, he has to take pi to be a self-dual Heck-Maskas form, and this is for SL3 over a number field. So he has to have the level 1, and it has to be a self-dual form. And finally, there's this breakthrough result of Paul Nelson, where he gets a subconvex bound for any L function for any number field. So it's more general for any GL1 twist and spectral aspect as well, but for this particular talk, I'm just concentrating on the T aspect. So I'm fixing the number field, I'm fixing the form, and I'm varying this parameter. Okay, so all of this history also just to get you up to speed with the different subconvexity estimates that have been established, the kind of rich work that you can see that's happening in this field. Right, so the focus for me is going to be GL2 over totally real number fields. Right. So going back to GL2, once again, over rational numbers, there's this result of Good, Merman, and Utila, who have established the wild type bound. And one of the ideas of delta method is you basically try and separate the oscillations, right? So if you look at the L function, you can of course expand it in its plane of convergence. But if you want to study it on the critical line, on the 1/2 line, you can approximate it by a Dirichlet polynomial of size, of length, square root of the conductor. And this, by approximate functional equation, you can approximate your L function at the 1/2 line by a certain summation like this, where lambda f n's now are the Fourier coefficients of the Gus form and enter the negative IT. So this T is the same parameter. There are various ways to go about it. One could take a moment of this and try to get a shifted convolution problem and then try to separate the oscillations. But of course, there is this well-known idea of Munshi that you can separate these oscillations right away in the L function itself without taking a moment of this. So you don't have to stick it in a bigger family. You can just take, you can just try to separate these oscillations. And you write the single sum as a double summation, and you try to get cancellations in this particular summation. And the choice of the delta method is very crucial. Once you choose the delta method correctly, you have to apply harmonic analysis. So you apply Poisson summation formula, Voronoi summation formula, maybe a large sieve or something like this, and try to get cancellations in this particular sum. And the main result that I'm going to give an indication about, and it's still a work in progress, is that if you take a Hilbert modular form of any level, any weight, and actually any central character as well, which is defined over a totally real number field k of degree d. Once again, I'm fixing this number field. Then the bound that you get is a wild type bound, which is t to the 2d over 6. And this is basically following this philosophy of Munshi and following the paper of Acharya, Kumar, Methi, and Singh over the rationals and making it over the number fields. So since I said one has to be careful about the delta method, and this is a delta method conference, let me also give a quick overview of the various delta symbols that are here. Okay, and maybe the soul of the delta symbol is an orthogonality relationship that detects whether something is 0 or not. That's something lying in a lattice. So over here we are looking at integers, and you can detect whether an integer is 0 or not using this particular integral, where the notation is that this e nx is e to the 2 pi I nx. So if you integrate this over the circle, you will get 1 exactly when n is 0, you will get 0 otherwise. And there are various delta methods floating around that people have utilized. One is the trivial delta method, which essentially takes this particular length and breaks it apart into arcs of length 1 over q. So the point being that the number of harmonics that you're using in order to detect whether a certain integer is 0 or not is q many. Over here, this k and this q are two parameters. And I did not write, but for this delta method to work, this parameter q has to be bigger than this parameter k. But the point is that if you look at these additive characters, there are q of those. On the other hand, you have a more powerful and more flexible, a more powerful delta method. This is because of Dieck-Friedlander and Iwaniec. For that, you should notice that there are now q squared many frequency as opposed to q many frequencies, q squared many additive characters as opposed to q many additive characters. Over here, this g is a certain weight function that determines how large this q and n parameters are. Okay. If you want to detect if two integers are equal to each other, you can just take their difference and ask whether that difference is equal to 0. And that way you can detect when two integers are equal to each other. So one can use these in application of subconvexity because you had a certain summation. There was an index in the Fourier coefficient and index in the IT, and then you can detect when those two oscillations are equal or not. But now going over number fields, there seems to be a little bit of a trouble in order to detect when two ideals are equal to each other. So now we have a very nice and powerful delta method because of Tim Browning and Pankaj Vishe. They looked at the DFI delta method and boosted it to the number field setting. So here the sigmas are the additive characters. Again, this gk is your weight function. And again, the point is that the number of these frequencies that you need are q squared many. Okay. So this is a version of the Dieck-Friedlander-Iwaniec delta method over number fields. And this detects when an ideal is equal to 0. The only problem is, as far as I'm concerned, I was not able to understand how to modify it to make sure that we're able to detect when two ideals are equal to each other. Because when you write the L function over number fields, you're summing over ideals. And if you want to now break apart these oscillations, you would like to detect when two ideals are equal to each other. And I was not able to do that, but there's something that comes to save us, and that's the Peterson trace formula. So this is the classical Peterson trace formula that I'm sure you will again see in this week, which basically can be thought of as a certain orthogonality or an approximate orthogonality relationship of the Fourier coefficients of cusp forms. So you can isolate the delta symbol over here, and you will get a certain sums of Fourier coefficients and certain sums of Kloosterman sums and the delta and the Bessel function. And credit where it's due, such an approach was suggested to me by Roman when I was doing my PhD. but then I did not quite follow it. And then much later, I'm like, okay, let's just get down to it and do it. So there is a Peterson trace formula over number fields, and we are essentially using the Peterson trace formula over number fields, and we are trying to make things work over here. Good. So a few comments over a few different approaches. Maybe this sigma is an additive character. It's very similar to, it's very similar to the DFI. Well, I cannot really say that A minus B is equal to 0. Like you take two different ideals, right? It's a difference of ideals. It's not quite making sense. Any other questions or comments? Right. Okay, good. Right. So a few comments over number fields, because I thought I will also tell you about the journey of arriving to doing these kinds of things, so that it kind of tells you the thought behind it. What you can do is start with the L function, apply the approximate functional equation, and approximate this particular L function by this. Now, please notice that the size of this Dirichlet polynomial is not t, but t raised to the d, where d is the degree of the number field. These lambdas are the Fourier coefficients, and this is the field norm over the rational numbers. And you can now try to separate these oscillations. So this is going to be the starting point. And now the challenges that we faced was, the first challenge was we're not able to detect when two ideals were equal to each other by the delta method that I just mentioned by Browning and Vichy. Second thing that you could possibly do is you can try to boil down this problem to the rational numbers. And now that becomes a little problematic. You have to really use the structure of the number field in that case. It becomes problematic because as far as the delta method is concerned, it seems to be extremely effective for lower degree L functions, but not really that effective for higher degree L functions. So if you let the degree of the number field be bigger than 1 actually, it starts giving you issues. Also the fact that if you look at totally real number fields, and you want to somehow sum over the ideals, you can try to first look at the class numbers. You can break apart everything in the cosets of class numbers, and there's an association of an ideal or ideal coset of the class group and a certain ideal. And you can do a one-to-one correspondence as long as you take that particular ideal and you mod it out by the group of units. The problem is that the ideals sit inside or an integral ideal sits inside the ring of integers very nicely. It's a lattice, but as soon as you mod it out by the group of units, it's not a lattice anymore. If, for example, it's a totally real number field, which is not the rational numbers. So these were some of the things that we had to deal with. And a few more words about boiling down to the rational numbers. You could start with this particular L function. And what you could, for example, do is instead of looking at GL2, you could just look at GL1 L functions maybe. So let these Fourier coefficients be actually just the Hecke mask, let these be a Hecke character and let's say an imaginary quadratic field. So the simplest possible case to try and deal with this. In that case, it will turn out that this L function is associated with a L function of a holomorphic form of a certain level and a certain Nebentipus, and we are able to get a subconvexity bound by classical methods. But again, as soon as you go to degree more than 3, it starts giving you certain issues. So that's why we were like, okay, can we try to circumvent all of these issues and try to deal with GL2L functions over number fields, but by using a delta method technique. All right. So I'm going to tell you guys about this work of Acharya, Kumar, Mathi, and Singh. They use this Peterson trace formula as a delta symbol, inspired by the work of Ritabrata Munshi for GL3 cross GL1. And they looked at this for GL2L functions. So they fixed this form and they looked at the T aspect bound. I'm telling you all of this over the rational numbers because that's much easier notation. And then I will try to tell you somehow, give you a motivation that yes, it does work over number fields. So once again, you start with an approximate functional equation like so. You want to now detect when two integers are equal to each other, and you can detect when two integers are equal to each other by writing this particular Peterson trace formula inside this. And if you do that, you can see that the trace formula is a difference of two particular objects. So on the one hand, if you stick in these Fourier coefficients, you will get a certain sum like this, where you are averaging over a basis of this vector space of forms, and you get these Fourier coefficients. Now, please notice that these lambda g's are coming from the delta symbol. So you have this freedom to choose this family according to you, and this f is fixed over here. And then you have this particular sum, which is this off diagonal, which has these Klusterman sums and this J-Bessel function right over here. So this is the starting of the Peterson trace formula as a delta method to GL2L functions setting. Good. So what's the steps? The first or the 0th step is that if you average over the weights, so once again, you can choose the family of this Peterson trace formula. So if you average over the weights, then you are able to make sure that this particular sum is as small as you would like. So you can get polynomially strong savings. So you can get a bound like t to the negative 10 million out of this, as long as the parameters satisfy certain bounds. So this parameter q is the level of the family that you're taking in the Peterson trace formula. This L are the weights, and this n is t to the d over here, where t is the t aspect and d is the degree. So as long as you choose this, you're able to do that. And then you are reduced to treating these terms that have the Fourier coefficients of all the different things. The first thing that you do is you apply dual summation formulas. So the dual summation formula to the n sums are the ones that have the Fourier coefficients. These are the indices of the Fourier coefficients. So applying a dual summation formula is akin to applying a functional equation. And you get on the other side a different length over here and a different Fourier coefficient. So if you apply the functional equation, so first you have to, so I should roll back and say things a little more properly. Over here, when I'm writing this particular sum, this is not a sharp sum. There's a smooth weight function that controls this particular length in a dyadic segment. You take that weight function, you apply Mellin inversion formula to that, and that's how you are able to get an L function. If you are careful, you apply the Mellin inversion formula so that the transform is fair enough, it's fairly to the right, then the L function converges. Then you apply the functional equation, and then you undo the process. And that's how you get a dual site like this. You can control its length. When you expand the L function, you can control its length as well. Once you get that, what you can do is you can apply Peterson trace formula again to the G sum, because there were certain lambda G's sitting outside with M's, and you have this G sum as well, which gives you a certain diagonal term, and it gives you a certain summation of Klusterman sums with Bessel functions. After that, you are going to evaluate the L sum, use stationary phase analysis. You have to evaluate chi sum, where chi was the Nebentipis of the family that you're choosing. Then you apply Poisson summation formula, then you apply Cauchy-Schwarz inequality, then you apply Poisson summation formula again. So there's a bunch of steps that you can do that Ritabrata did, that Saurabh and his co-authors did, and you were able to get a certain subconvexity bound. So I'm not going to, again, tell you all of those details, but my focus is going to be on the first few steps over the number fields case, and to try and tell you what are the kind of problems that appear for number fields and how we are able to get rid of those problems. So before I move on to the number fields, maybe I can take a quick pause and ask if you have any questions or comments. Why did I take the field to be totally real? Oh, that's just so that I'm able to deal with the Bessel function nicely. So far, the story I'm telling is for the rationals. So that's what I'll say next. So for reals, the Bessel function that you get is a product of your usual Bessel functions, the classical Bessel functions. Okay. So I need to tell you the setting of Hilbert modular forms. So let's K be a totally real number field of degree D, ring of integers OK, a different ideal del K. And what we'll do is we'll fix an embedding of this number field. And so it's a totally real number field, so it has all the real embeddings. You can define this group SL2K, which is again the group of these 2 cross 2 matrices, where now A, B, C, D are in your field. And the difference, oh sorry, I should have said that the difference is a unit, it's not just one. The difference is a unit. You embed this in this default product via the embeddings that you have fixed over here. And all of this acts on the upper half plane, the generalized upper half plane. So the upper half plane over here is going to be a product of your usual upper half planes. And this does act by the Mobius transformations. Since we have fixed the embeddings, you can, by fixing these embeddings, you can act on them by the Mobius transformations on each of these different D embeddings. Right, so this is the group action. You can prove it acts properly discontinuously. You can therefore have a fundamental domain, and you can talk about holomorphic curse forms and mass forms on that particular Riemann surface. Okay. You also have this J invariant over here that also satisfies the co-cycle condition as would happen in the case of rational numbers. And for that, therefore, you can define Hilbert modular forms. So if you take a subring, the subring that we are calling GL2 plus A is the ring of all these matrices in GL2A, such that it's totally real. So if you take this and you embed it, all these embeddings are they're totally positive. So all of these embeddings are going to be some real number that are bigger than or equal to 0. And you can define a congruent subgroup as well. So the congruent subgroup is going to be something that has certain entries where you want to make sure that these certain entries, the embeddings are totally positive. Also, you want to make sure that now this lower left entry is in, it somehow is divisible by your integral ideal. And you also want to make sure that there's the different ideal that appears. That's to make sure that the trace of this times, that's to make sure that the trace lies inside the integers. So you have to also take into account this different ideal. So that gives you Hilbert modular, that gives you a congruent subgroup, and you are able to define a Hilbert modular form as you would define almost for the rational numbers. So once again, please note that I am fixing these embeddings over here. Good. Over here, you can also have a weight, an associated weight of this. Right. Okay. You can expand this particular Hilbert modular form. Over here, it is not going to be a one periodic, but a different ideal periodic form. And you can then expand it into a Fourier series. There are going to be certain Fourier coefficients like so. These are going to be the additive characters that are associated over here. And you can write down its L function. So one of the notations that I will need is this particular narrow class group, which is, it's a narrow class group, so the notation is the CL plus. And given an integer ideal M, there exists a unique totally positive element inside the inverse of the different ideal, such that you can write that ideal as mu times T nu inverse. So essentially, you can have a representative of an ideal from the totally positive, sorry, not the totally positive, I'm sorry, from the narrow class group. Okay, good. So the point is here that you can associate an L function. It has an Euler product. It satisfies a functional equation. So you can look at the problem from rational numbers to totally real number fields. And you do have a Peterson trace formula. So the Peterson trace formula over here looks like this. This was definitely written out by Andrew Knightley and Charles Lee. They had this 2004 paper where they had a trace formula approach to Peterson, trace function approach to Peterson trace formula, but they did not quite explicate things over number fields. But in this paper of Tratobas, he did explicate things over number fields. And let me just quickly go over what are the different notations over here. So when I to answer your question, on the right side, you see this product of J Bessel functions. That's the Bessel function associated in the functional equation that you get. And it actually breaks down as a product of your usual Bessel functions. These LJs over here are the weights. You have certain harmonic weights, and this is a normalizing factor that appears right over here. This dk is the discriminant of the number field, and this is a certain Klustermann sum that I can tell you guys later about. And you are summing over certain ideals. And over here, because these are the classical Bessel functions, so you also want to make sure what is lying inside is a real number. So here you are summing over infinitely many units. So these epsilon j's, this epsilon j is the jth embedding of the unit epsilon. These alpha j's and beta j's are the jth embeddings of these numbers alpha and beta. So the script A and script B are ideals. These alpha and betas are just algebraic numbers that lie in inverses of A and B. So for example, if you take A and B to be integral ideals, you could very well take alpha and beta to be just equal to 1 and apply the Peterson trace formula. These alpha j's and beta j's are the jth embedding, so they are real. This ABC inverse squared in the brackets is the representative of this, so the representative of the ideal ABC inverse squared in the narrow class group. Because that's a principal ideal, and okay, again, I'm sorry, I'm missing, so there should be a sub j, so that's the jth embedding of that. Okay, so you have all of this, and right, okay, so this is a Peterson trace formula. Like average, like earlier, we'll have to average over certain weights. There's a caveat where later on, when we have to apply a certain functional equation, we do not know the root number explicitly of the L function when the Nebentipes is non-trivial for a Rankin-Selberg L function. But we are able to deal with that problem by introducing a conductor lowering trick. So again, credit where it's due. There was a bunch of us at AIM workshop last year, and while talking with the group of Ritabrata, Roman, Prahlad, and Jacob, they did inform me that there's a way to somehow go about this problem without really looking at averaging over Nebentipes by introducing a conductor lowering trick. So we tried doing that, and we were basically able to make things work. So we are trying to do that over number fields. Okay, so some calculations. Again, this is basically the setup where we are now separating these oscillations. So now we want to detect when two ideals are equal to each other. And we'll have an off-diagonal term and the term with Fourier coefficients. In the last 5 minutes, I just want to show you that we can actually also prove that the off-diagonal term that you get in this case is also going to be as small as you would like. Sorry, how much time do I have? Do I stop at 12:20 or 12:30?
You have until 1/2 past.
Oh, I have until 1/2 past. Ah, sorry. So I was hurrying up for nothing. I thought I had until 20. Okay, so I can go a bit slower, then I can explicate and try to really tell you how these things are working. So a few things and where these basically various terms are coming from. So if you observe over here, you do have a double sum that are averages over these indices. So if you apply the delta method, you will see the m sum and an n sum. That is coming from the approximate functional equation of the L function. And then the rest of the things are coming from your delta symbol. So you have this average over these levels coming from the delta symbol. And you have these averages over the weights, again coming from the delta symbol. And you will not see these coefficients of the Peterson trace formula because over here I'm just looking at the off-diagonal term. So you will see the Klustermann sums, you will see the Bessel function over here. And sorry, there's again a typo. There should not be an epsilon here, there should be a 1 over here. So I can also then tell you what the Klustermann sum looks like over number fields. So for A and B, that are C that are any fractional ideals, and you would like alpha in A inverse, beta in B inverse, C in C inverse. You can write a Klusterman sum, which is associated with alpha A, beta B, and C, which is going to be a sum over these particular classes. So you are summing over the ideal A. This is the different inverse and C inverse, modded out by the ideal A, the different inverse, and your small c inverse. So this, you have to do this normalization. Again, you can somehow imagine that you are summing over classes A mod C over here. And there is an additive character. So the additive character looks like this. So it's the e to the 2 pi I of the trace, the field trace of this particular thing, which is alpha x plus beta, and a class representative of A, V, c to the negative 2 x bar over c. And so this is what your Klusterman sum looks like over totally real number fields. And it does satisfy your bound, which is that it is less than the norm of the GCD of alpha A, beta B, CC to the 1/2 times this tau of CC times the norm of C to the 1/2, where I should tell you what this function is. Here, tau of M. So if M is an integral ideal, then this tau of M is basically the number of integral ideals such that you look at this fractional ideal Mn squared itself has to be an integral ideal. So you do have a Klusterman sum that does satisfy the Weatherlian bound that you have over here, and you can work with all of this. Okay, and so this is the kind of off-diagonal terms that you would see if you apply the Peterson trace formula. And what I will show you is that you can actually show that this contribution is negligible, modulo a difficulty, and the difficulty is going to be coming from the group of units. So if you looked at just the rational numbers, not a number field, the group of units is finite. You literally have 1 and -1. But over here, the group of units is infinite. Right? So the dimension is R1 plus R2 minus 1 in general. Here I'm taking totally real, so it's R2 is 0. So the dimension of the group of units is R1 minus 1. So you have infinitely many units as soon as you go to a totally real number field of degree 2 or more. So we will have to also be a little careful when we are bounding these particular sums that we take care of the infinitely many units. Okay. So what we will do, as was done by Ritabrata or by Saurabh, Sumit, and Acharya and Gopal Methi, right? So they considered the L sum, and they said that, well, you can bound this very nicely, and that is how you can show that you will end up with a very strong bound over here, which gives negligible contribution. So that's why I said there's a typo. There should be a 1. This Klusterman sum over here does not depend on the units. Over here, you will just have this. Right. So the first thing that one has to notice is that there's a summation outside and a product inside over here. And if you want to somehow treat things classically in parallel to how you would do classically, you would definitely like that the summation is inside and the product is outside. so that for each summation, you get a strong bound in the way that these guys have done, and then just take a product of all of those and you're done. But one has to notice that because these are sums over a dyadic interval, and each of these LJs are even, you can actually interchange the sums and the product, and you will still get the same thing. So that's the first thing that we do. So we have interchanged the sum and product, and then we look at each sum separately. And for that, we use Ivanits's lemma. So if A is congruent to plus or minus 1 modulo 4 and G is a sufficiently nice function, then you have a certain average of the J-Bessel functions, the weighted J-Bessel functions, in a certain form of this integral. And you are actually then able to isolate what the oscillations look like, and you're able to apply stationary phase analysis, or you're able to apply integration by parts. And as soon as these parameters satisfy certain conditions, you are able to get arbitrary savings. So that's the kind of thing that we also use. So if you apply this, you apply integration by parts, then you can show that for each embedding J, you will have this particular summation where H is a weight function that controls these LJs in a dyadic segment, and these LJ minus 1s are these J-Bessel function associated to the jth embedding. They satisfy a certain bound like this. And now what is this bound like? Well, the bound is this particular argument sitting right over here, divided by this particular length and to whatever power. So you take the square root of this particular entry in the J-Bessel function, and you divide by the length that you are summing over. Okay, so I have not really told you why that happens, but this is essentially applying this particular lemma. And you can get arbitrary savings, right? So you can do integration by parts some AJ number of times, and you get savings AJ number of, like to the power of AJ. What one has to notice is that then you go ahead, you choose these lengths correctly, and as soon as the norm of this C that you were summing over is big enough, it is bigger than x over QL to the 2D, where x is the length of, or the sizes of the norms of m and n's, these two things that you had separated in the beginning, you will get an arbitrary saving. So that first tells you that there is going to be a saving in the C sum, but you also have to contend with the epsilon sum. Right? So the sum over units will still give you an issue, because you will see that for each thing you have a saving which looks like, let's say, t to the minus 10 million. But if you sum infinitely many t to the minus 10 millions, that's still infinite. So for that, we have to make sure that the sum over the units also converges. And for that, we use the lemma of Vengi-Luo. So this is Luo's lemma. So if you take a totally positive unit, you can choose certain powers such that a certain sum of the product converges. Okay, so over here, how are we choosing? So if the jth embedding of this totally positive unit is less than or equal to 1, we choose this power to be 0. But if it is bigger than 1, you choose the power to be a fixed delta, which is bigger than 0. Okay, so you fix that. Then what happens is that if you sum over these infinitely many units, then this particular product does converge. So as an example, if you take all of these delta j's to be 1, the product of these epsilon j's will just give you 1, because that's the norm of the unit, and you sum over the infinitely many units, that's infinite. But if you raise it to good powers, you do get something that converges, and that's what we do. So we have to be, just going back, we have to be basically be careful about how you choose these AJs. So how many times you differentiate each of the jth embeddings is where we have to be careful about. And if you do that, we basically choose how many times you differentiate, let's say, A plus delta j many times, where A is now fixed and big. A is big and delta j is fixed, so that you have something like this. Then the product of all of those things can be broken down into two different products, where you just have these A's and where you have these deltas. And now, if you take the product, you see that taking the product over the j's gets rid of the epsilon j right here. Because if you take the product over here, you will get the product of all these epsilon j's raised to the a over 2. But the product of all these epsilon j's is nothing but the norm of epsilon, and epsilon is a unit, so its norm is 1. So that gets rid of the product over here, and you still have a product over here, which gets you to this. And now if you sum over the infinitely many units, that's not an issue. So there are a few tricks that you will have to do over number fields in order to make sure that the classical methods do extend over number fields. Okay, I'll stop there. Thank you.
Thank you, Keshav. We do have time for questions. Any questions for Keshav?
So I don't know if you've made it through this far yet and checking the computations, but in the case of GL2 problems and applying classical Peterson, it reduces to a trivial delta. Have you checked in the process if there's something that arises which is signaling?
So we are trying to do that. Of course, as you had realized somehow, there's a Warner formula that you can apply somewhere, and that gets you like a symmetry that you have to exploit. So application of the Warner formula was a bit of an issue for us because the Warner formula that we did see were written in adelic settings, and we had to then explicate it classically, and we had to also make sure that we are able to do it with level. And so we were not able to do that then, but this is something in parallel that we are running. So that's a very good question and comment that out of the Peterson trace formula approach, it will be nice to see a trivial delta method over number fields.
Yeah, okay, Gergely already has another question.
Yeah, obvious question, and sorry if this is naive or not appropriate, but how about more general number fields? Have you thought about them?
Not yet. So
where are the difficulties?
Sorry?
What are the difficulties to
So one of the difficulties is the estimates and the Bessel functions. So the Bessel functions that do appear in the functional equation for a more general number field will be different. And I've basically not started looking at all of these, but those will be, so for the complex embeddings, those are going to be something different. So I was with Naomi using certain estimates and certain functional equations that were given by Shimura. And Shimura was looking at Hilbert modular forms, where he had pretty much explicitly written down everything. For totally real number fields, again, as far as I know, the literature, things do appear, but they are in an adelic language. And to translate them in a classical language is something that we have not really looked at. It is entirely possible that one does not need to translate it, and one is actually able to do this approach over a general number field. But that is not something that we have looked at yet. That is also like an open direction that we would like to do and see what happens.
Okay, thank you.
Okay, any last question? Well, in that case, let's thank our speaker again.